Hi everyone, we're back for lecture 20. We're going to talk about nonlinear differential equations. So we've talked about nonlinear difference equations where time was discrete, now nonlinear equations where time is continuous. So we're all on the same page. Let's remember these definitions that we talked about previously. A first order differential equation is just y prime is equal to some function of t and y. And this differential equation is called autonomous if it doesn't depend explicitly on time. And it's considered to be linear if it can be written in a special form. If it can't, then it's nonlinear. We're going to talk about functions like that today. You may remember from your differential equations class that solving nonlinear differential equations was in general really difficult. But there was one form of those differential equations that was easier to solve, and those were differential equations that were called separable. Separable equations are when you could separate out the function of t and the function of y, and then you could write the differential equation in this form and integrate both sides, right? That was the plan. And when you did that, you found some function of y and t that looked like this with an integration constant that gave you an implicit definite, there's a typo here, implicit definition of y. Sometimes we could solve for y and get an explicit definition of y, but it doesn't matter if not. It gives us a relationship between y and t. And so these were differential equations that I could solve really easily. So let's just do an example. So this is separable, right? Because I can write it like y times y prime is equal to t, this differential equation. And then I can integrate both sides. So the derivative of y, or maybe I should write this step in case this was helpful. So if I think of this as dy over dt, this is y dy and then t dt, just to be clear. So the integral of the left-hand side is 1/2 y squared. The integral of the right-hand side is 1/2 t squared. We can just combine our integration constants here. This one we actually can solve explicitly for y, right? This is y of t is, let's get rid of the halves, and c is a constant. Doesn't matter if it's c or 2c, right? So we say that y is plus and minus the square root of t squared plus c. So this is the type of solution that we would look for. In this case, we said we want to have that y of 0, which is just going to be plus and minus the square root of c, is going to be 1, plus and minus 1. So we have y of t is c, so plus and minus 1. Yeah, that's fine. It's going to be plus and minus t squared plus and minus 1. So whatever these functions are. Great, so these are nonlinear equations that I do know how to solve. So let's look at an example of a separable nonlinear differential equation and think of it in terms of mathematical modeling. So we're going to look at a disease model, a very simplified one, that says, suppose we have some infectious disease that has affected 50,000 out of a population of 1 million individuals. And after 1 month, the number of infected individuals has gone up to 100,000. So let's find the number of infected individuals in millions after 2 months. If we assume the following model, let's say that the number of infected individuals increases continuously at a rate proportional to the product of infected and non-infected individuals. Okay, so how do we write this model? So we said we have 1 million people, right? And we want to write the population in millions. So it's going to be somewhere between 0 and 1. And we want that the rate of change, so I prime, is proportional to the product of infected and non-infected. So infected is I, and 1 minus I is non-infected. That's clear here from equation 7. And then the proportionality constant is K. So hopefully it's clear that I of t must satisfy this equation here. And let's consider an initial condition, or the initial condition of 50,000. Now if I'm writing it in millions, I have to divide by 10 to the 6, so I get 0.05, right? This is in millions. Great. So if I want to use separation of variables, this is clearly separable, right? I can write this as I prime divided by I times 1 minus I is equal to K. And then I can split it up with partial fractions. Oh, yeah, lots of typos today. I can split it up with partial fractions and then solve in the same way that I just did, integrate both sides. I'm not going to go through that here. That's something we probably did extensively in differential equations. So the general solution of this guy can be written in this way. Depends on the proportionality constant K and the integration constant C. If I want to plug in my initial condition, when I plug in 0 here, I get 1 over 1 plus c is equal to 0.05. So if I divide both sides by 0.05, multiply by 1 plus c, and then do 1 minus 1 over this guy, which is 20, or sorry, that minus 1, 20 minus 1, I get that c is 19. So the equation that describes the number of infected individuals at time t is this one here. I don't know K, so I can use the other bit of information in our problem that said after a month, 100,000 individuals were infected. When I plug 1 into this equation and set it equal to 0.1, I can solve that and get this K right here. So I plug that into my formula, and I know that e to the ln, those can cancel as long as it's only ln, so I can bring the t into the argument of the ln as an exponent. So it's e to the ln 9 over 19 to the t, and then I'm left with just this when the e and the natural log cancel. Excuse me. So after a year, let's just notice, if I plug in 12, this gets really, really big, pretty fast. And so if I plot it in MATLAB, I got a plot that looks like this. So it starts here at 0.05, and it goes up pretty steeply to 1, which is 1 million. So that was this maybe more general model where I was proportional with an unknown proportionality constant. Let's just consider an even simpler problem here that looks just like this. The proportionality constant is 1, and I have some unknown initial condition, y naught here. So in general, this solution is going to look like this. I no longer have my e to the minus kt, because the k is equal to 1. I don't see the k anymore. And then I solve here with my initial condition for my integration constant. So this is the solution in general, just written in terms of the stuff that you're given in the problem, the initial condition. So for example, if I chose an initial condition that was like 1 over 64, the plot looks different than the plot above, but not that different, right? So we'll look at this one. I guess you have the PDF. It's a little shallower, takes a little bit longer to rise, right? At 6 months, you're just over 0.8. Where here at 6 months, you're almost getting at 0.9. So it seems to rise more steeply here, even though it seems to start a bit lower. Yeah, hopefully that is clear from these pictures. So why do these have such similar shapes? Well, let's look at the analytical expression. If I want to calculate the limit as t goes to infinity, what happens? Right, as t goes to infinity, e to the minus t goes to e to the negative infinity, which goes to 0. So this goes to 1. So I'm always going to have some exponential growth settling to 1, to an asymptotic value of 1 as t goes forward. So So that's why the shape of these really look similar. So let's explore this more, but first let's recall that autonomous differential equations have this idea of an equilibrium solution. If I find a place where the y is constant, right? Which is equivalent to saying where the f of x, or f of y in this case, is equal to 0. That's kind of the concept here below, right? If y is a constant, the derivative is 0. The derivative is f of y, so I can just directly solve the algebraic equation. So with that in mind, if I look at the differential equation here, what are the equilibria? If I set this equal to 0, the equilibria are y are equal to 0 and y is equal to 1. These are the two constant solutions. If I put them in, I never change. So what can I say about their stability? I don't really have a concept yet of stability for a nonlinear differential equation in continuous time. So we're going to build that in this lecture. But first, let's think about how we can approximate solutions near these equilibria, right? Because stability is going to be a property that in general is local around an equilibrium point. And so, so let's understand what we mean by local. So I have, again, just looking at an autonomous system, and I have an equilibrium I want to approximate it around, call that YE, I can notice that f of y, the right-hand side of the differential equation, can be written by equivalently by adding and subtracting the equilibrium in the argument. But then I can do a Taylor expansion here, right? This is a first order Taylor expansion. First order Taylor expansion. And if I do that, that's just the function value at the equilibrium. We remember what that is, right? That's 0 by definition. And then added to f prime y at the equilibrium ye, and then y minus the equilibrium. So just left with that second summand here. So this linear approximation can be used to write this differential equation really as a linear differential equation, right? This is approximately this, the right-hand side. And this is a constant, right? So this is literally just a linear differential equation, right? This is why it's called linearization. And you should know this is like the bread and butter of what people in dynamical systems or people who study differential equations do when they have a nonlinear system. This is the first thing you do. You find the equilibria, you linearize near it, and you talk about what the stability properties are. So what we're doing here is authentically what people do. Just as a side note, what is the solution? What's the general solution of this linearized differential equation? Well, it's a linear differential equation. It has one solution at the equilibrium, right? And then the solution is going to look like the solution to this non-homogeneous differential equation, which is the solution to the homogeneous part, which is y prime is equal to f prime times y, yl, I guess, in this case. So that's this guy here. And then the particular solution. Right, this is the homogeneous and particular solutions. So that's what we've done before. Well, we reviewed it before. You've done it extensively before, I'm sure, in differential equations. Right, so linearization. That is the name of the game before you know what else you may be able to do with the problem. So forgetting that we know that this guy is separable, let's take a look at how we can linearize near these equilibria. Okay, so we need to find the derivative of the right-hand side, right? So what's the right-hand side? The right-hand side, f of y, is, I'm going to write it like this, y minus y squared, just because I think it makes finding the derivative a little bit easier. And so at y is equal to 0, oh, sorry, that's a prime here, yeah. Oh, wait, no, sorry, that's f. That's just plain old f. Now we need to find f prime is 1 minus 2y. Okay, now we're in business. So at the equilibrium 0, f prime of 0 is 1. So the linearized equation is YL prime is equal to 1 times YL minus the equilibrium, 0. Very boring. Very easy solution to write, right? This guy, C e to the t. Right, function that's its own derivative. Okay, what about at y is equal to 1? F prime at 1 is 1 minus 2, so minus 1. So YL prime, the linearized system, is minus 1 times y minus ye, which is 1, right? So this becomes 1 minus y. Hopefully that's clear. And so what's the solution here? The solution here, I have a minus in front of the y, so it'll be something like c e to the minus t, and then the equilibrium here is 1. So 1 plus c, oops, e to the minus t. There we go. Okay, hopefully that is clear there. Great. Okay, so let's look at plots of what these two linearized systems look like as compared to the real solution that we found using separation of variables. So here's a plot of the linearization near 0. So this is the exact solution, or the analytical solution. From separation of variables. See, we like a separable equation because then we can actually compare and see how good the linearization is. This is a linearization near 0. So remember, the linearization relies on a Taylor expansion. That is a local approximation. We can definitely see the effect of that here, right? We linearize near 0. So the approximation, the dashed line, it's a pretty good approximation for the solid line near 0. But when you get bigger than 2, 3, that falls apart completely, right? And of course it does, right? I have an expression here with a 1 over e to the minus t and some other junk versus just an exponential growth, which is what I get from the linearized function. As a comparison, oh, whoops, I guess in your notes I had a spot here to do the linearization near 1 in a separate place, but we already did it in the smaller space. So we can look now at the plot near 1. Oh, I'll write it again so we see it. So this is now 1 plus c to the minus 2. So if I look at this guy, now I see I get an approximation that looks good when I'm close to 1, right? So that, again, the real solution is solid and the dashed line is the linearization. So near 1, it looks like I'm approaching the same asymptotic value at 1. So it's a pretty good approximation, but farther from 1, it starts to get really, really bad. It matches up right at 0, but the rest of it is a pretty bad approximation. But, you know, it depends on what you need, right? If you want to piece together a bunch of local approximations, you can start to get a good idea of what's going on in the system. So remember, the question we were trying to get towards is stability. Now we have equilibria. We have linearizations near the equilibria. And so how do we talk about the stability of the equilibria using those linearizations and the concept of stability that we already built for linear systems? So let's talk about some definitions of stability properties. So if I have an equilibrium for this differential equation, call it YE, an equilibrium solution is stable if, for any epsilon greater than 0, there is a delta, so that every solution that starts within delta of the equilibrium never goes outside of a circle of radius epsilon for all t. Start close, stay close. I hope that makes sense. That's a crucial definition. If you're not stable, you're called unstable. If you leave this epsilon radius at some time, then you're not a stable solution. You can get arbitrarily far away from the equilibrium. If we have a stable equilibrium, we can also give it these two kind of stronger conditions. We've talked about this for difference equations and also for linear differential equations. This should be pretty familiar to you. A locally asymptotically stable equilibrium solution is one such that if I start within a range of delta, as t goes to infinity, all of my solutions are going to approach the equilibrium. So this is start close, not only stay close, but approach. So you will approach the equilibrium asymptotically. An even stronger version of this, it relaxes this condition on the fact that you have to start close. Those equilibria that satisfy this are called globally asymptotically stable. So if any solution approaches the equilibrium and the limit as t goes to infinity, it is a globally asymptotically stable equilibrium. Just as a note, if a solution is globally asymptotically stable, hopefully it's clear that it is also locally, but the reverse isn't true, right? Locally doesn't imply globally. So these are increasingly stronger conditions. So now that we have this concept, let's talk about this, this theorem here. So the theorem says, let's let A not equal to 0 be a real number. So I have a differential equation, linear, right? It has a unique equilibrium at the at YE, right? That's what makes the right-hand side equal to 0. And furthermore, if A is less than 0, then any solution is going to approach the equilibrium, which is globally asymptotically stable. So page breaks here. And if A is greater than 0, then for any epsilon, I can find a solution that gets greater than epsilon away from the equilibrium. And will get arbitrarily big as t goes to infinity. In this case, it's unstable. So when I have this simple linear form of a differential equation, all that matters is the sign of A. So why is that? For that differential equation, I can explicitly write the solution, right? This is the solution. So if A is negative, this term vanishes as t goes to infinity, and the whole solution goes to YE. If A is positive, this term blows up. It's pretty simple to see. So that's just for a linear differential equation, and we've actually talked about that before. Not exactly in that nomenclature, but we've seen that before. But now we can relate this to nonlinear differential equations through linearization. That's our theorem 2. So let's say I start with a nonlinear differential equation with an equilibrium. If I linearize to the equilibrium, this should now look to you exactly like that linear equation from the theorem above. So what do we know? We know now that all we have to know about is the sign of this f prime at the equilibrium to talk about the stability of equilibrium. So if f prime is less than 0 at the equilibrium, then the equilibrium should be locally asymptotically stable. We'll never be able to say something global because, of course, linearization in and of itself is a local concept. And the second part, which says, what if the equilibrium is greater than 0? Well, it's greater than 0. Sorry, f at the equilibrium is greater than 0. Then we have an unstable equilibrium, right? We have an exponential function with a positive epsilon that blows up. Okay, I hope that's clear. So if I go back to my example now with my two equilibria, are they stable or unstable? Well, we showed that for at 0, f prime, for the equilibrium at 0, f prime was equal to 1. So 1 is greater than 0, which implies unstable. And at 1, we had f prime was equal to -1, which is less than 0, which implies a local asymptotically stable solution. Okay, I'm going to stop the video and we'll come back and do one example.